Good evening, dear students. Okay, we will proceed with Laplace transform. Okay, so today the first topic that we'll be doing is Laplace transform. Laplace transform. Laplace transform of periodic functions. Just a second. Okay. So first let me write it. If t be a periodic function, of period t, that means f of t is equal to f of t plus t is equal to f of t plus 2t dot dot. Okay, then Laplace transform of f of t is equal to integration 0 to t e to the power minus st f t dt divided by 1 minus e to the power minus s capital T, right? So this is the Laplace transform of a periodic function. So we'll now try to prove it. Proof. Okay. So Laplace transform of a function, if we straight away apply the definition, we have 0 to infinite e to the power minus st ft dt, right? Now you can always break the functions into periods, so it is 0 to t e to the power minus st ft dt plus t to 2t e to the power minus st ft dt plus 2t to 3t e to the power minus st ft dt and so on, right? Now our motto will be to change the limit from 0 to t. So we are going to make substitutions, right? In the second integral, we are going to substitute u is equal to t minus capital T. In the third integral, we are going to substitute u is equal to t minus a 2t, right? And so on. In all the integrals, we'll be substituting like this. So after substituting, what do we get? We get 0 to t e to the power minus st ft dt plus integration. Now we put the limits, so t minus t becomes a 0 and this 2t minus t becomes a t. So we have achieved our integral limits. It becomes e to the power minus s. In place of t you can write u plus a capital T f of u plus a capital T dt du plus it becomes 0 to t e to the power minus s u plus a 2t, right? F of u plus 2t du plus dot dot dot. So now what we have is e to the power minus st ft dt plus it's the integral over d of u, so you can obviously take the constant part outside. E to the power minus st we can take outside, 0 to t e to the power minus s u, and since it is a periodic function, f of u plus t is equal to f of u, right? So we can write f of u du plus plus you take the constant outside, e to the power minus s 2s t integration 0 to t e to the power minus su fu du plus dot dot dot, right? So now you can write is equal to integration 0 to t e to the power minus st ft dt plus e to the power minus st integration 0 to t. You can always change all the u's to t's, right? So minus st ft dt plus sorry, again I've done the same mistake, minus 2 st integration 0 to t e to the power minus st ft dt plus so on. So now we can see that this portion 0 to t e to the power minus st ft dt is common in all the terms, so we'll take that out and we have 1 plus e to the power minus st plus e to the power minus 2st plus dot dot dot, and we have 0 to t e to the power minus st ft dt, right? So this comes up to integration 0 to t e to the power minus st ft dt divided by 1 minus e to the power minus st, since we know 1 by 1 minus a is equal to 1 plus a square. This is well known to everybody, and so it is proved, right? This is what we wanted to prove, that the Laplace transform of a periodic function is given by this. Okay, so we will do few problems so that you can understand how it works. I have been repeatedly telling you, please practice problems, as much problems as possible. Okay, I'll start with a very simple one so that you do not face any problem to grab it. Okay, question. Find the Laplace transform of the periodic function if t is equal to e to the power t, 0 less than t less than 2 pi. That means our time period is 2 pi. So the solution is Laplace transform of ft. Since ft is a periodic function, the Laplace transform is given by 0 to t, over here t is 2 pi, e to the power minus st ft is equal to et dt divided by 1 minus e to the power minus s into capital T, that is over here 2 pi, right? So now you just need to perform this integration. 1 minus e to the power minus 2 pi s 0 to 2 pi e to the power t 1 minus s dt. So just do it. It is very easy now. 1 minus e to the power minus 2 pi s, and you have is e to the power 1 minus s t divided by 1 minus s 0 to 2 pi is equal to, now just put the limits. In the denominator we have the constants out, 2 pi s and 1 minus s, right? 1 minus s, in place of t we have 2 pi minus, and when it comes to 0 it is 1. So this is our answer. So whenever you are given any periodic function, this is a formula you need to apply and solve the problem. Okay, we'll be solving one more problem. Question. Find the Laplace transform of half wave rectified sine wave given by if t is equal to sine omega t and 0. Sine omega t, it is from pi by omega, and this is from pi by omega less than t less than 2 pi by omega, right? If you need to solve this, what needs to be done? Okay, so the Laplace transform of the function is given by, the denominator we have 1 minus e to the power minus s t. The t over here is, it's a complete period, so the time period is 2 pi by omega. So you have a 2 pi by omega, and in the numerator you have 0 to t, that means 0 to 2 pi by omega, ft e to the power minus st dt, right? So it comes up to e to the power minus 2 pi s by omega integration 0 to, we'll break it into two parts obviously, so it is pi by omega sine omega t e to the power minus st dt plus a 0, right? So all you need to do is perform this integration. I'll do it for you, but it's a simple integration, you all know it. You have been doing this all throughout your 12. Okay, so we want to solve e to the power minus st sine omega t dt, right? So the first function constant omega t, integration of second function st by minus s, right, minus integration ddx of first function, that means omega comes out, cos omega t, and e to the power integration of second function, so you get this minus s dt, right, plus we have integrated that, so the constant has already come, is equal to e to the power minus st sine omega t, a minus sign comes in front and we have a s, right? This minus comes out, so it becomes omega by s. We need to integrate this part again, so it is first function constant, integration of second function minus ddx of first function minus sine omega t, integration of second function minus s dt plus c, right? So over here you have I is equal to minus, can you see? Yes, you can, e to the power minus st sine omega t by s. Okay, we bring this term outside, so minus omega by s square cos omega t to the power minus st, and over here you have 3 minus, so it becomes a minus we have omega square, right, and the s square in the denominator, s square integration sine omega t e to the power minus st dt plus a c, right? Now this we had started with this expression e to the power minus st sine omega t, so this is what our I was, so we can take this term this side and take I common, so taking I common, what we get is 1 plus omega square by s square is equal to, okay, we can take e to the power minus st by s square common, so minus e to the power minus st by s square common. If we take that, we get over here s sine omega t plus omega cos omega t, right, plus a c. Or I is equal to minus, okay, the s square cancels from both sides and the denominator we are left out with s square plus omega square, so we have minus e to the power minus st divided by s square plus omega square s sine omega t plus omega cos omega t plus a c, right? Okay, so now we just need to put the integration limits, so integration 0 to pi by omega e to the power minus st sine omega t dt is equal to Okay, if you put these limits over here, pi omega goes, so the sine term completely cancels out, it becomes a 0. We are left out only with the cos term. So we have in the denominator, okay, we have this minus and s square plus omega square. Inside the sine term is completely gone, we have the cos term, so it becomes e to the power minus s pi by omega. The omega is there and this cos becomes a minus 1 and minus, for 0 it becomes a 1, right? Omega is there and a 1. So it comes up to omega, we can take common, s square plus omega square. Both has minus sign, so it cancels out, minus s pi by omega plus a 1. So this is our final. Now we have to, therefore we put it in the Laplace transform of the function. So Laplace transform of ft is equal to 1 by 1 minus e to the power minus 2 pi s by omega into omega by s square plus omega square e to the power minus s pi by omega plus 1, right? So over here we have e to the power minus s pi by omega plus 1, and over here we have 2 pi s by omega, so it is 1 s square minus b square. If we apply that, we can cancel out the numerator term and it ends up to omega s square plus omega square. The plus term gets cancelled, so we are left out only with the minus term, so it comes up to 1 minus e to the power minus pi s by omega, right? So this is our answer. So this is how you need to solve all the periodic problems. If you are asked to find the Laplace transform, this is the formula where you need to put all the periodic functions and solve it in this way, right? Okay, now we are moving on to a very important portion, and that is the convolution theorem. Convolution theorem. Okay. First, I'll state the theorem. I'll write the theorem and then I'll explain it to you. Okay. So, if Laplace transform of a function ft is equal to fs and Laplace transform of a function gt is equal to gs, then Laplace transform of the convolution of ft and gt is given by the Laplace transform of the individual functions, or equivalently inverse Laplace of fs gs. If you apply inverse, you should get the original function is ft dt. This is a very important formula. You will need it a lot to find the inverse of various functions, inverse Laplace inverse of various functions. Okay, where ft convolution gt is called the convolution of ft and gt and is defined by the integral ft is the symbol of convolution is equal to 0 to t f of t minus tau g tau d tau. Okay, so we will be proving this theorem. So first, you all have done convolution theorem during your Fourier transform lessons, right? So you have a fair idea of what convolution is, but still if you want to understand what the convolution of two functions is, this is the definition of convolution of two functions, right? So if you're asked to find out the convolution of two functions, what you do is you keep one function as it is, like over here gt has been kept as it is, and you reverse the other function. See, gt has been changed to minus tau, that means it has been reversed or reflected, and then it is shifted by a amount t. Okay, so what we do is first we take a dummy index. Instead of t, now we have kept tau. We keep one function as it is and reverse the other function and then shift it by amount t, and then the multiplication of the integral of the multiplication of those two functions is called the convolution of two functions, right? This is what convolution means. Now the convolution theorem in Laplace transform states that the Laplace transform of convolution of two functions is equal to the product of Laplace transform of the functions themselves. Okay, this is a very important theorem. This will be very helpful when you need to find the inverse Laplace transform. Okay, if you can write this, obviously you can write this, that is, if the Laplace transform of this is this, so obviously the inverse Laplace transform of this has to be this. So this theorem can equivalently be written like this. Okay, so now we'll prove the convolution theorem. Let's see how to prove it. Okay, I'll do it in the next page, I guess. Okay, so we have by definition Laplace transform of convolution of two functions is equal to 0 to infinite e to the power minus st dt, and the function over here is the convolution that is defined by ft minus tau g tau d tau. I hope this is understandable. Now the function over here is this, because we have defined convolution like this, right? Now please try to understand over here that the region of integration over here is this, okay, tau t. The region of integration is this. What I mean to say is, first the integration is done over tau, right? Integration is done over tau. That means first we go from tau equal to 0 to tau equal to t. So this is our tau equal to 0 line and this is our tau equal to t line, right? So first what we do, first we perform the integration over tau. We move from tau equal to 0 to tau equal to t. That means say we move from here to here, okay? This is what we perform first. We do not cross this line, okay? So the region of integration is always below this line. And then what we do, then we perform the integration on t, and t moves from 0 to infinite. That means then we move this vertical column from 0 to infinite, right? So first we do this integration. That means we move from tau equal to 0 to tau equal to t, because these are our limits. And then what do? We shift this vertical column or the vertical strip from 0 to infinite. We move this way. So we covered this region. So what I mean to say is the region of integration is this. Now what we intend to do is we intend to change the order of integrations. Okay, so if we intend to change the order of integration, what we need to do? This same thing, this same region can be done if we consider horizontal strips as well, right? Tau t. So now first we want to perform the integration on t, right? So if we want to perform the integration on t, we need to move t from where? This is the tau equal to t line, right? So we need to move t from tau equal to t to infinite, right, to cover this strip. and then this strip needs to move from 0 to infinite. Okay, so I don't know if I would like to repeat over here. That is, initially our order of integration has been integration on tau first and then t first, but now we want to change the order of integration. Okay, we want to do the integration on t first and tau later, second. Okay, so if we now our region of integration is always below the tau equal to t line. Now we can do it now we can also do it using horizontal strips, right? So what needs to be done? Now the region of integration, now the limits of t needs to be from this to this. That means from t equal to tau to t equal to infinite, first we'll go from this region and then we will shift the horizontal strip from 0 to infinite, right? Then the same purpose will be served. So what I was saying is, now we will do it like this way. If we are just changing the order of integrations. Okay, we now change the order of integration. Okay, the explanations are given in the PDF. You need not write right now. So if we change the order of integration, equation 1 becomes, this is equation 1. Equation 1 becomes so now we want to bring the tau in front, so g tau d tau, and we want to take the t at the back, f of t minus tau dt, right? Our integration limits will be, this t needs to vary from tau t equal to tau to t equal to infinite. Any strip you consider, if you consider this strip, it will move from here, it will start from t equal to tau and it will end to t equal to infinite. So our limit is t is equal to tau to t is equal to infinite, and then the strip needs to move from down to all the region below the tau equal to t line, so it needs to go to infinite, from 0 to infinite. So this is so the order of integration has been changed. Now all we need to do is, we want to substitute this as z, substituting t minus tau is equal to z. What do we get? 0 to infinite g tau d tau. So now this becomes 0, right, and this becomes infinite, e to the power minus s z plus a tau f z, and dt becomes dz, right, is equal to, this tau portion comes in front, so 0 to infinite, e to the power minus s tau g tau d tau, 0 to infinite, e to the power minus s z f z dz, right? So this is nothing but the Laplace transform of g tau, and this is nothing but the Laplace transform of f z. So you get what you intended to get, right? So we have Laplace transform of convolution of two functions is equal to the Laplace transform of the functions themselves, proved. Okay, so this is a very important formula. Like I am saying, you will need this a lot when you need to calculate the inverse Laplace transforms, so try to understand it very clearly. I'll be solving one or two problems and I'll be wrapping up today's class. Okay, so question: find the convolution AT. This is question number 1 and this is question number 2. You need to find out this convolutions, right? So if you want to solve one, AT, by definition we can solve it in one line. 0 to t, you have to select one function which you will keep as it is, and you have to select another function which you will reverse and shift. Okay, so we are keeping t as it is, so we keep tau, and this function we are reversing and shifting it, so it becomes a t minus tau, right? This t has been changed to t minus tau d tau. So your constant terms comes out 0 to t tau e to the power minus a tau d tau. So all you need to do is perform this integration. This is your homework, please do it. I won't perform it now. Okay. The second one, the convolution of this, you can obviously write it as this. So first we do the convolution of this two, and then we'll do that of the third one. So this can be written as, you keep one function as it is, so you keep t as it is, and the second t you change it by t minus tau, that is you reverse it and then you shift it, d tau t. So over here you get t square minus a t tau t minus, okay, sorry, I have written this wrong. This is going to be tau. I'm so sorry. One function you keep as it is, that means you have to write it a tau because we have to change it to a dummy index, and the other you have to reverse it. So over here it becomes, very sorry. So over here it becomes 0 to t tau t minus tau square d tau, sorry, the t. So the t is a constant and goes out. If you perform this integration, it will come up to t cube by 6, and then you have to do this convolution again with this left out t. So now it becomes 1 by 6, 0 to t. Obviously we'll keep the t cube as it is, and the simpler term we will reverse, and tau cube and t minus tau. This we have kept this t cube term as it is, so it has been written as tau cube, and this t we have written as t minus tau because we have shifted it and we have reversed it and then shifted it, right? So now you have to do this integration, and I'll just give you the final result. The result will be this. These integrations are your homework. Okay, so I'll wrap up today's class. If in case you have any confusion regarding today's class, please do let me know and practice all these theorems. I'll meet you in the next class. Thank you.